Now, in this video, we will be looking at a property of elements, ionization energy. Now, when we consider any neutral atom of any element and we remove an electron from that atom, we will be left with an ion. Now, the amount of energy required to remove 1 mole of the most loosely held electron from 1 mole of gaseous atoms to produce 1 mole of gaseous ion is what ionization energy is all about. So we'll be looking at the general trends or patterns of ionization energy of elements on the periodic table and also look at the factors contributing to this trend or pattern. Now, as a general rule, the ionization energy of elements increases from left to right and also up the group. So we would expect an element like carbon to have a higher ionization energy compared to lead, and we expect germanium, for example, to have a lower ionization energy compared to bromine. But there are exceptions to this general rule. There are some anomalies across the periodic table. Now, group 2 elements and group 13 elements show this exception to this general rule, and group 15 and 16 elements also show exceptions to this general rule. As you can see on the graph provided to my right here, you see beryllium and boron is showing exceptions, and we see nitrogen, oxygen also showing exceptions on the second period. We see magnesium, aluminium showing this continuity here, and phosphorus and sulfur also showing an anomaly. But in general, you see that there is increase in the ionization energies across the period. From lithium to neon, there is an increase, general increase in the ionization energy, and from sodium to argon in the third period, we see a general increase in the ionization energies. But what is accounting for that? Now, let's consider period 3 for our exercise, from sodium to chlorine. The ionization energy of sodium is 495.8 kilojoules per mole, as against that of chlorine, which is 1246. So you can see that if you move across the periodic table from sodium to chlorine, there is an increase in their figures, in their ionization energy figures. But we would like to know what is causing that. Each element on this period has 3 principal quantum energy levels. The outer valence shell, which is receiving the incoming electrons, is the same as you move across the period. The 2 inner lower energy shells contain a total of 10 electrons, 2 in the first energy level and 8 in the second. So each element has 2 lower energy shells with a shielding constant of 10 electrons, shielding of part of the nuclear charge. So as the atomic numbers of these elements increases, their proton numbers also increases, because the atomic number is an indication of their proton numbers. And as the proton numbers increases, the charge on the elements also increases. So as the atomic numbers of the elements increases, their proton numbers also increases, their charges increases, and their effective nuclear charges also increases. Now, sodium is the 11th element on the periodic table. It has a shielding constant of 10 electrons. So sodium has an effective nuclear charge of 1. So sodium with 11 protons with a shielding constant of 10 electrons has an effective nuclear charge of 1. Now, magnesium is the 12th element with 12 protons, a shielding constant of 10 electrons, an effective nuclear charge of 2. Aluminium silicon is the 14th element, phosphorus, sulfur, chlorine, so you realize that as you move across the periodic table, the effective nuclear charges also increases. Now, according to Coulomb's law, the force is proportional to the charge. So here now the question is, what is the effect of the increasing effective nuclear charge as you move across the period? Now, so the effect of the increasing effective nuclear charge on the valence shell electrons is that it causes the shrinking of the atomic size and a decrease in the atomic radius. So as the effective nuclear charge increases, the force of attraction from the nucleus of the elements also increases and forcing the valence shell electrons more strongly toward itself, attracting the valence shell electrons more strongly, binding them more strongly to itself and more tightly to itself. And when that happens, it would require more energy to remove the electrons from the atomic structure. So here the factors that we'll be considering is the nuclear charge. When the nuclear charge increases, the atomic size decreases. The shielding effect, though important, it is not a primary factor over here because it plays less significant role compared to the nuclear charge in the overall increase of the effective nuclear charge, because the screening effect is relatively constant as you move across the periodic table. So as you move across the periodic table, the effective nuclear charge and the atomic size plays a very significant role in determining this phenomenon where the ionization energies of these elements increases. The greater the charge, or the greater the effective nuclear charge, the greater the force of attraction from the nucleus on the valence shell electrons, the greater the binding force and the greater the attraction of the valence shell electrons by the nucleus to itself more tightly, and makes it difficult to remove an electron from its atomic structure, and hence the greater the ionization energy. Now, as you move down the group, considering group 1, lithium has an ionization energy of 526. Potassium, which is 2 steps below, has an ionization energy of 425 kilojoules per mole. Now, each step down the group is added a principal quantum energy shell. This means an increase in the shielding effect. And so down the group, atomic radius increases and the distance of the nucleus to the valence shell also increases. Now, according to Coulomb's law, the force is inversely proportional to the distance from the charge. And so the greater the distance of the valence shell electrons from the nucleus, the smaller the force of attraction on them, the smaller the binding force on them. And so the weaker the nuclear influence and the weaker the binding force on them, the less energy is required to remove electrons from them. So as you go down the group, the nuclear charge and the distance of the valence electrons from the nucleus, and of course the shielding effect, plays a very important role in determining or rationalizing the decrease of the ionization energy values of elements down the group. You should take note that with lithium, there is one lower energy shell below the outermost shell. With sodium, we have 2 lower principal quantum energy shells with a shielding constant of 10 electrons, and with potassium we have 3 principal quantum energy shells below the valence shell, which is containing 1 electron. So these are the reasons why the ionic energies of elements show that trend, and these are the reasons that accounts for why the ionization energies increases gradually from the left of the periodic table to the right, and also decreases as we do go down the group. So this is the end of my video. Thank you for watching, but keep watching.